Well, hello. As promised, we're going to electrochem, and I promised that we would use the oxidation reduction parts, and I would also tie this into thermodynamics. So, aren't you excited? Okay, so electrochemistry, and before you right here, I have a voltaic cell. So, what I have, well, at least a picture of it, a two-dimensional representation of a voltaic cell. I have an anode, in this case it's zinc, and it is electrically connected to the cathode, in this case copper metal, and I have the anode sitting in a 1 molar zinc ion solution. And I also have the cathode sitting in a 1 molar copper solution. And in between them, I have a salt bridge. A salt bridge is something that, in this case, is potassium nitrate. When you make it, you kind of take a solution and you put a cotton ball in it, and you stick the cotton ball in it, and you have the counter ions. Potassium nitrate is a common one because it's very soluble. Okay, and so if I were to connect this together, what will happen is that the anode will get oxidized. So I hook up the battery and get everything electrically connected and put in the salt bridge. I will have a voltaic cell, and the anode will corrode. The anode will oxidize. Zinc metal will turn into zinc plus 2 ions and give off 2 electrons, and then the electrons will flow towards the cathode. And then on the cathode, the electrons will attach themselves to the copper plus 2 ions in solution, and then the cathode will grow. The ions will be reduced, and the cathode will grow in size. And then the electricity is running this way. So the electrons are running this way, and in doing so, we can use them as they flow to do work. So you can use this electricity then to run your cell phone, to have a drone fly, to light a light bulb. And the amount of energy I get from this is exactly 1.1 volts. Well, I shouldn't say, oh, that's the potential. That is the potential of the electrons flowing. So let me talk a little bit about some of the units and what this means. So you might see circuits like this before. The battery here, the long end is a positive and the negative end is the small one. And all the circuit diagrams that you see, they are modeled such that the positive charge is the one that moves. It turns out the positive charge doesn't move, it's the negative charge. The electrons are the ones that move. So why did we do this? Well, when Ben Franklin did this back in the early 18th century, I shouldn't say early, I guess it was middle to late 18th century, he didn't know if the positive or negative moved, so he guessed. And you know what? He guessed wrong. And we know that he guessed wrong. Have we gone and changed it? No, we have not. We still model everything as if the positive charge is moving because we like to stick with our mistakes even when we know they're wrong. But so whenever you're reading a circuit diagram, we are just so consistent with our guesses, and then going with it, we just haven't changed it. So everything is based off the positive charge moving, even though the negative charges move. The other thing, though, you think the electron, so you're just going to go back to the voltaic cell. Does that mean this electron here is going to be going over there? Not really. The electron doesn't really go that far. The electrons, typically, they move on the order of 10 to the minus 5 meters per second. That means all day you might go a centimeter. So the electrons are not moving very fast. There is something called the electromotive force, and that moves at the speed of light. So the electromotive force, it's a photon driven process, so photons move at the speed of light. Electrons themselves don't move all that fast, at least in a linear fashion. They themselves can move very fast, but not that fast. Okay, so the battery, it's wrong. This squiggly line that I put an R above that's known as a resistor. These two lines right here, this is known as a capacitor. So a resistor resists the flow. A capacitor, it's kind of like a storage. So it's a A capacitor, it stores charge. You have two plates, one's negative, one's positive, and it just charges it up. And then it can shoot out a really fast burst of current. Think of it like a parking lot. Think of the battery as like a car factory, and think of the capacitor like a parking lot. So you can throw, and think of the cars as the current flow. So the factory over a long period of time will generate lots of cars, but you can store cars temporarily in a parking lot, and then you can have access to a lot of cars real fast. Likewise, a capacitor, you can have access to a lot of current real fast. And what do we use things of capacitors like? Like the flash on a camera. That's from a capacitor. Some capacitors are used, just to give a big oomph of charge really quickly. So whenever you need a quick process, that's what capacitors are for. This 3 lines, this is known as the ground or the earth if you are in a different language. And this squiggly line is called an inductor. This is a DC circuit. If you are here in the United States and we have the AC circuits, we have, this is the plug. I've emphasized it a little bit. The little tiny plug is the positive or hot terminal. The longer one is the negative or neutral terminal. And then the circle in the middle is the ground. Okay, so the way alternating current works, it goes up and down actually, and the hot wire, that's the one that sparks. Also, generally speaking, the positive terminal is the one that sparks. If I were Ben Franklin, I had to guess between the positive and negative, which one would move. I would have guessed the positive too, because the positive terminal in the battery, it's the one that sparks. So it's moving the negative one isn't too scary. The positive one, I'm always kind of scared when I take apart my car battery because you put it on, you hear the electronic discharge from that. And likewise in your plugs in your wall, your hot wire, that's the dangerous one. You can get shocked from your neutral, but the hot wire can really, really shock you. Also be careful, in some places, like train tracks, sometimes the train tracks themselves are the neutral line. Sometimes the metal casings in street lamps, and also even the sewage, like manholes, metal manholes. Some of those are actually neutral lines for electricity. So be careful when you start randomly touching metal objects. If it's not grounded properly, you might be touching the neutral line. You might get shocked. Usually doesn't kill you, but it might be a little bit of a jump. Pets the same way. Sometimes pets walking around, they're not wearing shoes, and sometimes they step on things like manhole covers and they get shocked. So anyways, I mentioned volts. The volts is a joule per coulomb, and so I mentioned current. Current is a coulomb divided per second. So I think of it like a river. Okay, so think of a river of water flowing, and a coulomb, that's the amount of charge. Okay, so later on we'll talk about Faraday's constant. There are 96,500 coulombs in a mole of electron. So, or an electron has a charge of negative 1.6 times 10 to the minus 19 coulombs. So coulomb is the SI unit for charge. So current is the amount of charge per second. So like in a stream of water, current would be akin to the amount of water that's flowing in a stream. So the current is the amount of charge that's flowing through the wire. And then the voltage is the potential. In the wire, it's how much energy each electron has. So the amount of energy per charge. So in the stream of water analogy, it's how fast the water is moving. So you can have a very slow moving stream and a very fast moving stream. The fast moving stream is the one that has the higher potential, the more potential energy. And power is of something is the voltage times the current. I know this is not a physics class, but I'm trying to connect these concepts for you. This is not on any of the tests. Volts being joules per coulomb and amps being coulombs per second is, but power is not. Power is energy divided by time, and the unit for energy joule divided by seconds is a watt. So a watt is a joule per second. So when you hear a watt, that means an energy of 1 joule per second. Okay, so hopefully this ties some things together. And I mentioned this voltaic cell, so let me go back to show you. Here's the voltaic cell again. Okay, and there's a couple things with this voltaic cell. If I make one in the laboratory and I see it's 1.1 volts, you're like, you know what? What if I go into my backyard and I get a piece of zinc the size of a compact car and a piece of copper the size of a compact car, and then I go and I put these in two of those standing up pools, like you see the commercials for those above ground pools, and in the zinc one I put the 1 molar nitrate, zinc nitrate, and in the other one I put the 1 molar copper nitrate, and then I go and I get a big PVC pipe and I fashion this salt bridge, and I get this. I soak a T-shirt in potassium nitrate and I stick it in there, and I've got this huge salt bridge. I connect them and I have the two wires together. I'm like, all right, I'm gonna get this and have this huge voltaic cell, and I'm gonna hook it up to the voltmeter, and I hope the voltmeter doesn't explode. And if I touch the terminals on the voltmeter, I will see 1.1 volts. So this amount of energy it's an intrinsic variable. It's kind of anticlimactic. That battery will run a very, very long time because I've got that huge amounts of anode, and I've got that huge pool-sized solution of the cathode, and that's when the battery dies, is when the anode corrodes away or all the solution gets reduced. Typically speaking, the anode corrodes away. That's usually what kills the battery. But that huge battery is not going to give you any more than 1.1 volts. So the E0, the standard potential for the cell, and this is going to be in volts, joules per coulomb, is the energy of the oxidation, the E0 of the oxidation plus the E0 of reduction. And so oxidation reduction, the potential for the oxidation is minus the potential of reduction. So what we've done is we have this chart here, the standard electrode potentials at 25 degrees Celsius. You do not have to memorize this. This will be provided for you. But you notice you have fluorine on the top, and you have the various things, and then you have lithium on the bottom, and they have numbers. What we did is we picked a 0, and the 0 we picked was hydrogen. So we said that hydrogen plus 2 electrons to form hydrogen gas is our 0 potential, and we make this relative to the rest of them. So that means that fluorine is 2.87 volts higher in reduction potential than hydrogen, and in the bottom lithium has the lowest reduction potential. But that also means that lithium has the highest oxidation potential, so which we'll show you next. So if you look here, so use the tabulated standard electric cell potential to calculate the cell potential for the following reaction. So aluminum plus nitrate plus 4 hydrogens makes aluminum plus 3 plus nitrogen monoxide plus 2 waters. So I've gone ahead and I've shown you in the chart, but let me show you that I've gone aluminum goes to aluminum plus 3 electrons. So that's the opposite of this here. So you can see aluminum going to aluminum plus 3 electrons going to aluminum is minus 1.66. But the other way around, aluminum going to aluminum plus 3 electrons, that is a positive 1.66. And so what we do is we just add these together. So let's see here, 2, there's a 1, 2.62 volts. So the standard cell potential for this one is 2.62 volts. And if you're wondering how do we get all these higher voltage in batteries, there's some tricks we'll talk about a little bit later. You can put them in series. So each of these series will be 2.62. You can put many of these in series and you get as high voltage as you want. Okay, so then we can predict whether reactions are positive or not. So I always think, well, this is coming up next, but remember the Gibbs free energy we talked about last chapter? If Gibbs is 0 at its equilibrium, if it's Positive, it's non-spontaneous. If it's negative, it's spontaneous. Well, the Gibbs free energy is minus n, the moles of electrons, times F, Faraday's constant, times E0 cell, the electric cell potential. So because of this, if the E0 cell is positive, it's spontaneous. It's spontaneous. And if it's negative, it's non-spontaneous. So the E0 cell being positive. So we have to see if it's positive or not. So let's look at iron and magnesium. So iron, Fe solid, and magnesium plus 2. So does it tell you which ion? To iron plus 3 and magnesium plus 2, or plus, sorry, iron plus 2, the magnesium metal. Okay, so if you look, here is iron plus 2, and here is magnesium. So magnesium going that way, it's negative 2.37, and iron, we're going to flip that. It's going to be positive 0.45. Adding those together, we're going to get close to negative 2. So this one here, the E0 is negative, that means it's non-spontaneous. So what I always thought about this, and maybe it's kind of juvenile, but I used to watch WWF wrestling. Maybe I'm showing my age. I used to watch WWF wrestling when I was a kid, and like Macho Man and Hulk Hogan and Ultimate Warrior and Andre the Giant, The Undertaker, $1 Million Man, all those wrestling folks. And I mean, of course, it's all fake. I mean, everything you know about that, it's all fake. But I mean, you always knew who was going to win before the match. So when Hulk Hogan fought Andre the Giant, you know Hulk Hogan was going to win. I mean, you didn't. I mean, of course it was. Anyways, same thing with this. It's like I can imagine, like, are you ready to rumble? In this corner we have iron. In this corner we have magnesium. Is this going to react? Who's going to fight whom? This would actually be a throne match because magnesium is just not good enough that can beat iron. But let's look at the other one. Look at iron and lead. So we have iron solid. Instead of that, let's look at lead plus 2. And lead plus 2 is right here. And so lead plus 2 electrons is going to be minus 1.3. But then iron going the other way is plus 0.45. That's going to be a positive 0.32. So this one here, E0, is positive. Therefore, it's spontaneous. So since that E0 is positive, this is, in fact, so this one is negative. So E0 is negative, no reaction. This one here, E0 is positive. You're like, yes to the reaction. Yes, reaction, sure. Yes, reaction. So lead plus 2 will, in fact, corrode iron. So if you throw iron and magnesium ion, absolutely nothing will happen. If you throw iron and lead plus 2 ion, the iron will corrode, and the lead will be reduced. Okay, so which metal dissolves in nitric but not hydrochloric? I'm sorry, which metal dissolves in nitric acid but not hydrochloric? So iron, silver, iron, gold, and silver. So we have to go back to this chart. So if you've noticed now, anything above it, so with iron, the metal, so iron metal, any ion that's above it, and I guess there's another iron right here, so anything above this for iron, it will corrode. And acid is directly above it, so iron will corrode an acid. And then if we look in silver, here I'll use pink for silver. Here is silver, and gold is kind of yellow. Here is I'll do yellow for gold, and if you look at this, so just plain old acid, silver will not react with acid. Although, if you do have this one here, I'll use blue. If you notice in this one here, nitric acid has both hydrogen ions and NO3, and that's above the line for silver. Therefore, silver will react with nitric acid. It won't react with any acid, but it will react with nitric acid. And so silver will dissolve in nitric. Gold will not dissolve in nitric acid. You can get gold to dissolve. You have to use something called aqua regia, which is a mixture of hydrochloric and nitric. So which one will dissolve in that? It's the silver. And the argument there is in the chart, and it's also the E0 is positive for that one. Okay. And then I already mentioned this, the delta G0 is minus NF E0 cell, and N is equal to the number of moles of electrons transferred. F is Faraday's constant, 96,495 coulombs per mole electron, also a joule. A joule is a joule per coulomb. Okay, so is this reaction spontaneous? So we have iodine, solid plus 2 bromides makes 2 iodides in bromine liquid. So I went ahead and looked up the cell potentials for you from the chart. So we have to figure out the E0 cell. So iodine, this is the one that is written as is. Bromine is going the other way, so we're going to put a minus sign here. So it's going to be 0.54 minus 1.09. So this will be 5, yeah. So this is going to be minus 0.55 volts. Okay, and you already know, we already know it's non-spontaneous. So, but let's go ahead and apply this equation. And the N equals 2 moles of electrons, because you can see here 2 moles of electrons. So this way, if we flip this the other way, 2 moles of electrons will be consumed. So N is 2 moles of electrons. And let me plug this in the equation. Delta G0 is equal to minus 2 moles of electrons. I'm using this equation here. Minus 2 moles of electrons times Faraday's constant, 96,485 coulombs per mole electron times minus 0.55. That's an ugly, let me rewrite that for you. Minus 0.55. A volt is a joule per coulomb. So the coulombs cancel. Let me do the units. The coulombs cancel, the moles electrons cancel, and we're left with unit-wise joules. And let me just put that in my handy-dandy calculator. A minus is going to be a plus. And let's see here, calculator. So 2 times 96,485 times 0.55, and this is positive. I don't need the positive, I'm just using it for emphasis. 106,133.5 joules, or how many sig figs? I'll just 106 kilojoules per mole reaction. So, like so. So positive 106. So recap with this one. So we're given this equation. Using the tabulated values there, we keep iodine as is, but we have to flip the bromine, and then we calculate the potential then to be negative 0.55 volts. We apply that equation. The delta G0 is minus NF E0 cell. N is the moles of electron transfer. In this case, it's 2. So delta G0 is minus 2 moles electrons times Faraday's constant, 96,045 coulombs per moles electron, times negative 0.55 volts or joules per coulomb, and then we're left with 106 kilojoules per mole positive, and this is non-spontaneous because it's a positive delta G. So what do you think about this one? Why don't you think of this one, and let's hopefully you remembered back to this one. This one is positive. It's the opposite of this one. We've just calculated this one to be the opposite direction. And this one here is, well, it's the opposite direction of that one. So it's just going to be the opposite direction of that. So it's going to be the same answer, but negative. So, but if you want to go and calculate it through the long way, go ahead. But I did this because you need to underestimate the sneakiness. You sometimes gotta be a little lazy. Think about where you can do shortcuts here and there. Okay? All right, so we're done with this section. I will continue on with equilibrium in the next section.